Hello, welcome back. We have been discussing the first unit of applied physics, that is quantum mechanics. In this video, we'll discuss the effective mass of electron. We have seen the behavior of an electron that is moving through a periodic potential. The EK diagram of an electron that is moving through the periodic potentials. When an electron that is moving through a periodic potentials is accelerated by electric field or magnetic field, then the mass of the electron is not as that of the rest mass of the electron. The mass of the electron moving through the periodic potentials under the influence of external electric field or the magnetic field is called the effective mass. When an electron in a periodic potential of lattice is accelerated by an electric field or magnetic field, then the mass of the electron is called effective mass. Effective mass is denoted with Nm star. Since the charge of the electron is E, small e, suppose the applied electric field intensity is capital E, then the acceleration is given by A is equal to minus E capital E upon m star. Electrical force on the electron is F is equal to m star A. In this expression, we are using an m star here to indicate that it is the effective mass of the electron. Since we are talking about a free electron, quantum mechanically speaking, which is a wave packet. A wave packet means a group of waves. Velocity can be represented using the group velocity. The velocity with which the group moves is called as the group velocity. It is represented with a Vg. We write Vg is equal to d omega upon dk, where omega is the angular frequency and k is the propagation vector. Vg can be written as 2 pi d nu by dk, where nu is the frequency, that is the linear frequency. But we know that E is equal to h nu, so you write this as 2 pi upon h dE upon dk. This can be written as 1 over h bar dE upon dk, because h bar is equal to h by 2 pi. From velocity, one can write the acceleration as A is equal to dvg by dt, which is equal to 1 over h bar d square E by dk dt. We write this in this fashion: 1 over h bar d square E upon dk square dk by dt. And we know that h bar k is equal to p, the momentum, and the force F is given by dp by dt. One can write this expression as dh bar k upon dt, that is h bar dk by dt, or dk by dt is equal to F, the force upon the h bar. So we write acceleration A as 1 over h bar square d square E by dk square F, which implies F is equal to h bar square upon d square E by dk square A, which means we have come to the expression as F is equal to ma. This is a similar expression. Here On the left hand side we have the force, on the right hand side we have some quantity times acceleration. Then the quantity should be equal to the mass. We call the mass as the effective mass. So the effective mass m star is equal to h bar square upon d square E by d k square. We call this 3. In this, h bar is a constant. This indicates that the effective mass is determined by d square E by dk square. We shall now see how the energy is going to vary with k. If you recall the EK diagram, the first Brillouin zone is from minus pi by a to plus pi by a. So in the first Brillouin zone, the energy is going to change as a function of k. In this plot, we have represented the energy versus k. So energy is going to change as a function of k in this fashion. We shall now see variation of group velocity with k. Here you see at the middle we have 0. As k increases, the group velocity increases. The group velocity reaches a maximum value here, which corresponds to k0. And similarly, when the group velocity of the electron in the opposite direction also increases, you see that it reaches minimum value at minus ka. After increasing the value of k beyond this point, one notices that the group velocity decreases and it eventually drops to 0 at plus pi by a and minus pi by a. The points where the group velocity starts decreasing is called as the points of inflection. For k is equal to k0 corresponds to point of inflection. Up to the point of inflection on the positive side of the k, the group velocity increases. Beyond the inflection point, even if k is increased, the group velocity decreases. And eventually it becomes 0 for k is equal to pi by a and k is equal to minus pi by a. Next we shall see variation of effective mass with k. In this, at 0, we have the mass which will be equal to rest mass of the electron, that is m. As the value of k is increased, you notice that the effective mass starts increasing slowly, and at the point of inflection, it suddenly changes from positive mass to negative mass. Beyond the point of inflection, if k is increased, it slowly starts increasing and reaches some value here. At the inflection point, the effective mass suddenly becomes negative, and for k is equal to pi by a and minus pi by a, it will have certain negative mass. Beyond the value of k0, even if you increase the k, one notice that the effective mass is going to increase and reaches some value for k is equal to pi by a and k is equal to minus pi by a, which means at these points the acceleration is negative. Which means from k0 to pi by a and minus k0 to minus pi by a, the lattice is exerting a large retarding force on electron. This means in this region the electron behaves like a positively charged particle. And this positively charged particle is referred to as a hole. In this video, we have started our discussion with movement of electron in a periodic potentials and EK diagrams. When an electron in a periodic potential of lattice is accelerated by an electric field or a magnetic field, then the mass of the electron is called effective mass. Effective mass is denoted by m star. If charge of the electron is E and the applied electric field intensity is capital E, then the acceleration is given by minus E capital E upon m star, and the electrical force on the electron is given by F is equal to m star A. A free electron is considered to be moving through the lattice in the form of a wave packet, and a wave packet is nothing but a group of waves, and the group of waves, they move with a velocity which is called as group velocity, represented by Vg, and we have obtained Vg as 2 pi d nu by dk. We have also written Vg, that is the group velocity, as 1 over h bar de by dk. The acceleration is the rate of group velocity, that is dvg by dt. We have obtained the acceleration as 1 over h bar d square e by dk square dk by dt. Since we know h bar k is equal to p, we have written f as h bar dk by dt. From this we have written the acceleration as a is equal to 1 over h bar square d square e by dk square f. The force is equal to h bar square upon d square e by dk square into a, which means the effective mass is corresponding to h bar square by d square e by dk square. So the effective mass corresponds to d square e by dk square. We have seen how the energy of the electron is going to vary with k. From the EK diagram, minus pi by a to plus pi by a, the first Brillouin zone. In the first Brillouin zone, the electron energy is going to change as a function of k in this fashion. The variation of group velocity with k is as shown here. For 0 value of the k, the group velocity also is 0. When the k is slowly increased, one notices that the group velocity also increases slowly and reaches a maximum value for a k value that is called as k0, and after that, even if the k is increased, the group velocity slowly decreases. This point on the positive side and on the negative side is called as point of inflection, where the velocity slowly starts decreasing. For k is equal to minus pi by a and plus pi by a, group velocity again becomes 0. We have seen the variation of effective mass with k. We have said that as the k is increased, the effective mass also increases up to the inflection points on either side, k0 and minus k0. Beyond the inflection points, the effective mass suddenly changes to negative. The sudden change in the effective mass is explained using the force that is exerted on the electron by the lattice. In this region, that is from k0 to pi by a and minus k0 to minus pi by a, the electron is considered as a positively charged particle, and the particle is generally referred to as a hole. Thank you.